This is our next topic. Probability. You know what probability is
Yes.
and what is that?
Probability, like the chances of something happening.
Very good. Chances
The
of something happening. Normally, we'll call that an event in
Mhm.
mathematical term, an event. Chances, possibility, occurrence of something to happen, we will call it event. Event is basically um, anything you mention. Suppose we are playing with the dice and we say that an even number will occur. So that is the event explained and what will be the probability, we'll calculate it. Now probability scales, that would depend which scenario we have. Like we may be talking about probability distribution or frequency distribution. Then what are the trials? For example, I throw the dice once or I throw the dice twice. If we are playing with a coin, I toss it and I may get head or tail. And what if I toss it twice or thrice? So those are trials. The experimental probability is the one which we actually perform. And
So like,
theoretical probability is the one which we are talking about.
oh, so like experimental is like more accurate?
Experimental is the real probability.
Mhm.
And you may say yes. So what is the main difference between them, or what is the time? What is the situation when both of them are same? Okay, let's talk about this first and then we'll move on. Okay, so we have experimental and theoretical. Have you ever played Ludo
No,
board game? Dice. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Never? Do you know about it?
no.
Okay.
Wait, maybe use Monopoly. Like
Yeah,
as an
sort of.
example.
Sort of. So basically, we have a dice and they are numbered 1, 2, 3, 4, 5, and 6. Now, forget the board game. We have this dice. What is the possibility that when I throw this dice, I will get a 6 on top? May I say
It's
the probability? Yes, yes, sure.
1 out of 6.
1 out of 6. Now, if you're holding that dice and you throw it, are you certain that you'll get a 6?
No.
We may get anything. Then you throw it the second time. It may not be 6. The third time, fourth time, fifth time, sixth time, 13 times. That is quite possible in the real world that we might not get 6. Is it so?
No, I think, well, it's still the same probability all throughout.
Probability. That's theoretical probability. Theoretical probability. If you just
Oh,
hold a coin, that's head and tail. 50-50 chances. I say it would be head. You say that will be tail. And if you throw it 3 times and we still get a tail, I'll say I'm not that lucky.
sorry?
I'll say I'm not that lucky. I chose head, you chose tail, and you threw it 3 times and you got tail. So
Hmm.
theoretically, we do have a 50-50% chance. But in the real world, it may not be the same.
Oh, okay.
But what actually happens is we tossed the coin 3 times and we got tail. But if we increase the number of times, it will actually be closer to theoretical value. For example, actually we did that 100,000 times. And let me say head was 46900 and tail was the remaining times minus 46900. So that is 53,100. And when I divide any of these, I'm getting 0.469. If I just round it off to one significant, that is approximately 0.5. And this is 0.5310. That is approximately equal to 0.5. When the numbers become large enough, experimental values will start getting equal to theoretical values. We discussed a real life example of pizza.
Yeah.
Keep that in mind whenever we order, suppose 9-inch pizza, and the manager offers you two 5-inch, that is not the compensation. Even if he offers you three, still that is not the compensation. This is
Only
another real life example.
so
Just wait for that day
experimental.
when he offers you two.
So experimental is real, but unless we do it many times, it's gonna also match with the theoretical.
Yeah.
Theoretical more so works with like the numbers of it, like the actual probabilities, like the
Yes.
percent.
What we will do here and what we will do in the real world, we'll always calculate them.
Mhm.
And we will calculate and give this data to someone for whom this is useful and who that might be. For example, let's say we bought some seeds and we want to plant roses, and we have A type, B type, and C type of seeds. A type person says that one seed will cost you $10. This person says that one seed will cost you $1. And the last one says that one seed will cost you 0.60. Now, what is the difference? We are planting roses. Why is this expensive? This person claims that there is a greater chance to get a black rose. Ever seen that?
No, but I
Only
suppose it's
red?
the other ones. No, I haven't. But I think it's the rare ones, right?
Yeah, red, black, white. And I think I've seen purple as well. I'm not sure that was purple or faded, but I've seen these.
I thought like the ones with the other colors, like except for white, they would dye them. Like I know like the blue and stuff, they're dyed. I didn't know there was a black one.
Yeah, there is. In your free time, do look around.
Mhm.
Here in my country, we actually have an exhibition every year for flowers.
Oh, wow.
I actually saw it there. Okay.
Wow.
Coming back to this fact, for example, this person claims that this seed is expensive because he's saying there is a high probability that you'll get a black rose. Not in every seed, but there's a high probability that you'll get a black rose. And for example, we are getting red in the other two. So we already know that we are buying seed for $1 and we are selling the rose for $2. We know we are making a profit. And so will be the case in C. But if we talk about A and we say, what if we still get a red and we'll sell it for 2, we are at a loss of $8. Now, the person should, I'm not actually making an assumption of the probability. I just want to prove my point. So the person who is claiming that this is expensive, let's say he says there's a 70% chance that you'll get a black rose. That means more than half. So if we are purchasing 3 seeds, we may end up with 3 red roses when we grow them. If we are purchasing 300,000 seeds, yes, the probability will be closer to the theoretical value. The experimental, the actual probability will be closer to the theoretical value, provided we are talking to someone authentic, someone reputable. So for who is this data important? When we talk about something at the government level, again, if we talk about Pakistan studies, I have not read world history. So if we talk about that, we talk about agriculture. These are small lands and different person they own them. Let's say these are 9 different owners. Once the government imposed that no land should be less than uh, 1000 for sorry, not more than 1000 for unirrigated and 500 for irrigated lands. And larger the field, maximum number of seeds could be sown. In that case, farmers did this. They collaborated with each other. So when they're plowing the field, the one in this A section was plowing here and then U-turn, then again, then U-turn. And this person is using the same tractor and so is saving the fuel, so is increasing the number of seeds, and so is getting closer to the facts. So if I visit that shop and buy only one seed, I may end up with red rose. And if I buy more number of seeds, yes, I may increase my chance to get a black rose. So that happens in the real world. If you just place you ever played the darts game?
No,
Do you play any games? Outdoor
I
games?
do the
Okay.
board games too, but they're not really the ones with dices, except for like Monopoly, maybe. But
Okay, you would know about bow and arrow.
yeah,
So if we are just thinking about, if you have not played it, you may think that if you are given 4 trials, you may hit the target. But if I increase the number of trials? What if I allow you to do it 12 times? Is the chance of hitting the target increasing?
yes.
So the probability increases when number of trials are increasing. The theoretical calculation and the experimental value, let's say I'm talking about my domain, my subject, mathematics, and I say that my student, she can hit the target, allow her. I say that there is a chance that 50% of the time she'll hit the target. So people around us are saying, okay, 4 trials. And Milam take all those 4 trials and she hits the target 0 times. And I say, please allow to increase the number of trials. Now we are increasing the number of trials to 100. Still, we may miss the first 25, but we've practiced it 25 times.
Mhm.
26th time, maybe you'll hit. Now you've practiced it 26 times and so on. When you increase the number of trials, your chances of getting the target also increases.
It becomes more accurate. Like the theoretical data becomes
Accurate,
more.
yes. Good thing in our syllabus is that the probability is fixed. It is not changing with practice. And in the real world, it is fixed. Plus, when we keep on doing it, it improves, but only with large numbers.
Mhm.
Okay, so basic probability, simple formula, simple concept. You already know that number of times, this is the formula, number of times the desired event happens over total. Or we say number of success divided by number of trials. Okay, let's discuss basic examples and we'll move on to the concept. Stuck. Let me reopen it. For example, you have a dice, again, numbered 1, 2, 3, 4, 5, and 6. And we throw a dice. What is the probability to get even number?
3 out of 6.
Very good. So that
So
is
one.
1 by 2. What is the probability that you'll get an odd number?
Yeah, same. 3 by 6, 1/2.
6, that is 1 by 2. What is the probability that you will get a number which is greater than 4?
2 out of 6.
2 out of 6. So that is 1 by 3. What is the probability that you will get a number which is prime?
1 half?
Half, yes. 2,
Yeah.
3, and 5 are prime. So 3 out of 6. Yes.
1 half. 1 half.
Now I'm increasing the number of dice, or let's say the number of trials. I'm throwing it 2 times. When we throw it 2 times, I have to discuss the event. We may have different possibilities. We call it possibility diagram. So let's say on x-axis, this is the first trial. 1, 2, 3, 4, 5, and 6. On the other side, 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. So this may be a possible outcome. When we throw the first die, we may get 1, and we may get 1 on the second as well. 1 on first, 2 on second, 1 on first, 3 on second, and so on. How many total outcomes will we have?
6. Oh,
6.
36?
6 times is 36. Okay, now I'm going to place the question. And the question is, what is the probability that we get a same number on both the dice? Probability, same number on both the dice.
1 out of 6?
Yes. The purpose of this possibility diagram is actually that we can highlight 1, 1, 2, 2, 3, 3, and so on. Yes, this is 6 by 36 and 1 out of 6. What is the probability that you get both odd numbers? That this is the matter of presence of mind. Fresh mind, person is not sleepy, person has practiced, or one may do it as I'm doing. I'm writing it on the page, so reducing my thinking level, reducing the stress. So both are odd. May I just do it with you because I have that control of writing. So if I talk about the 1 or at the base, so odd is 1, 1, 1,
Yeah.
3, 1, 5. And then I reject this. And then when we talk about 3, again, we are having 3 odd numbers. So either we encircle all of these or we just pick up the pattern and I can see these are 9 out of 36 is 1 by 4.
Okay.
Now, what is the...
So,
Yeah, sure, sure.
like, if you're not like that much like familiar with it, you draw this,
We always
but
do
then
that.
yeah.
We always do
If
that. Students, they do ask me that what will we get at the end? And my first response is good marks. We will avoid careless mistake.
Mhm.
This is known as possibility diagram. Sometimes the examiner would tell you in the question that draw the possibility diagram. Meanwhile, we study. This is one diagram. Second is tree diagram. We'll study that. There is another shape of possibility diagram that is mostly given. That is very easy. And fourth is called as named as sample space. What is sample space? All those numbers which you were thinking before you answered 1 by 6 is sample space. I said same number on both the dice. So you may be thinking about 1, 1. You may be thinking about 2, 2. So these are the samples. This is known as sample space. 4, 4, 5, 5, 6, 6. Now what happens if I forget 1? The answer is incorrect. I lose the mark.
So it's
So
best to draw like this.
it's best to draw because we uh, can get 100% marks on this topic. And by just ignoring the fact that it will take us 30 seconds to draw, We're not risking it. Okay,
Purple.
both even numbers.
Oh, yeah, 9 out of 36 the same, 104.
9 by 36, same. 1 by 4, yes. Okay. Now, second shape is this one. I'll just reduce the numbers. Let me say that this is a tetrahedral die. Tetrahedral is with the four shapes, triangles on both sides and triangle at the bottom. Numbered 1, 2, 3, and 4. And this would look like this. 1, 2, 3, 4. 1, 2, 3, 4. In exam, we might have it for 6, just saving some time. And this is the question. It says plus. It says the event is we throw the dice twice and we add up the numbers. The result is the number which lands on the floor and we add up these numbers. So when we add 1 plus 1, we get 2. 1 plus 2, we get 3, 4, 5. As soon as we pick up the sequence, we just speed up. 2 plus 1 is 3, 4, 5, 6. 3 plus 1 is 4, 5, 6, 7. 4 plus 1 is 5, 6, 7, 8. When you actually get to solve this question, this is fun because that's easy. You just fill in the spaces. Now, probability that you get a number, you get a score that is greater than 5.
6 out of 16
Very good.
or 1 out
And
of
we always simplify, okay? Because we have calculators with us, he may penalize. If this is 1 mark question, he'll give the full mark for both of these. But if it is a 2 mark question, he will require simplification. And so is the case. He'll keep on changing his wordings and may ask part 1, part 2, part 3 on the same question. Like prime numbers, odd numbers, more than 5, less than 5, multiple of 3, and something like that. So we just read it carefully and we go through it. We haven't discussed a tree diagram yet. We'll come through the topic. Okay. What is this worked example? This is that dart and board.
Oh,
Suppose
oh, yeah, I think I know that one. Yeah, I think I know it. But I've never played it. I know it though. Okay.
that's actually really fun when you think you can do it and you never get it.
Must be very hard.
It never worked out for me. I just have one hanging there, but it never worked out for me. Suppose that blindfolded man is asked to throw a dart at a dartboard. If he hits the number 6 15 times out of 125 throws, what is the probability of him hitting? So possible outcomes divided by total. 15 by 125, we get the answer. Is the concept clear? This is a worked example.
Yeah.
So basically what we'll be dealing with is theoretical probability only. We are not performing it. In My brother went through intermediate computer sciences and they had a practical of this. They were given the dices and they were asked to throw and write all the sample spaces. So they used that and threw that on their table 100 times. And actually, not a single student was honest, obviously. They just wrote 5, 5, 6, 6, 7, 7, random. And there are tests, there are formulas that you can tell that they actually performed the experiment or they just wrote it.
Well, the test must have been like 5 hours for them to give you 100 times to do the dice.
Uh, Whenever you have practicals, you
Mhm.
have only two or maximum three questions.
Oh, okay.
Yeah, that's only the practical day.
Okay.
Okay, so theoretical probability is the one which we've been doing. An unbiased die is thrown and the number on the upward face is recorded. Find the probability of obtaining a 3. 1 by 6. Does it make sense? An
Mhm.
even number, already discussed. Prime number, already discussed. A card is drawn from an ordinary 52 card pack. Okay. One thing, these are the books which have been already published. Uh, Once there was a question in syllabus code 4024. That is O-level maths, and we are studying IGCSE. Question, the student actually um, filed a report against Cambridge that I never played cards. I've never seen cards in my life. How can you place a question? So there are 4 cards of each number. Have you ever played cards? Have you ever seen them?
I've seen them.
Okay. So there are 4 cards. If you see number 1, there are 4 cards. If you
Hmm.
see number 2, there are 4 cards. And there are 13 such examples. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's queen and something. 9, 10, 11, 12, 13. But there are 13. I remember that there are 13. I've also never played this.
There's 13 total like chances of cards.
Like total types. How many ones are there? 4. How many twos are there? 4. How many threes are there? 4. And
Okay.
if I make that list, we have 13 different type of cards.
Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9. One is basically the ace. And then we have king, 4 cards of king, 4 of queen, 9, 10, 11. I can't remember the other two, but there are 13. And let me cross check. 13 into 4 is 52. Yes. So he's talking about what is the probability that the card will be a king. So if you have that pack, there are 4 cards and total is 52.
Mhm. So
4
4 out of
divided by total.
so 1/13.
Yeah. Jason has 20 socks in drawer. 8 socks are red. 10 socks are blue. 2 socks are green. If a sock is drawn at random, what is the probability that it is green? So green are 2 out of total.
1 out of 10.
1 out of
Yeah.
10. The 9 painters are assigned a letter from the word Hollywood for painting at random. Find the probability that a painter is assigned a letter Y. So this is Y. That is 1 time out of how much?
9.
1 out of 9. Letter O,
2 out of 9. Oh, 3 out of 9.
3 out of 9. So that's the probability. Now look at this. H or L.
So that's basically adding them to like
Yes.
together.
Again, 3 out of 9. And
Yeah.
letter Z,
No, 0.
0 out of 9. 0. Okay, the probability that it even does not happen, obviously, that is going to be 0. And in the other way, if I just tell you that how many even numbers, I have few numbers at random, they're not in sequence. Like for example, 3, 9, 12, 14, 15, 17, 93, different numbers. So I'm telling you that the probability for even numbers is 1 by 7. So what will be the probability for odd numbers?
6/7.
Very good. total probability is always equal to 1. So what you did was 1 minus 1 by 7. So if there are only two cases, we know one probability, we can subtract it to find the probability of the other event. For example, I say that I am playing a cricket match with my friend and I have a chance of winning, that is 60%. So his chance of winning is 40%. Or may I say I have a chance of winning 60% and his chance of losing is 60%.
Mm-hmm.
Okay. Exercise. A sample die is thrown 100 times and the number 5 appears 14 times. Find the experimental probability of throwing a 5, giving your answer as a fraction in its lowest term. So I'm getting 5 up 14 times divided by 100. Any question in your mind regarding this word, experiment?
No,
I
real
said
world.
that what we are doing here is theoretical, but in this question, actual data is given.
Mm-hmm.
So 14 by 100, and we simplify it to 7 by 50. And you see, the question tells you to do it in its lowest term. When it is stated, yes, the examiner will penalize if someone writes 14 by 100. He or she has to do 7 by 50. Okay, the diagram shows a spinner that is divided. This is the spinner 1, 2, 3, 4, 5, 6, 7, 8. And the diagram shows a spinner that is divided into exactly 8 equal sectors. Ryan spins the spinner 260 times and records the result in the table. So how many times is getting 1? That is 33, 2, 38, 3, 26, and so on. If we just ignore the question and look at the spinner, may I say the chance to get 1 should be 1 by 8.
Mm-hmm.
Chance to get a 5 should be 1 by 8. And if we look at the table, are these numbers same?
No.
They're not same. So if we will increase this number to a very large number, they will eventually be close to each other.
How large does it have to be like considered more accurate? Like
Okay,
what's the
I'll be honest.
minimum?
I'll be honest. I've done O levels, A levels, then civil engineering, then masters. This field, if someone pursues this field of probability and statistics, will actually do mathematics, BS mathematics in his bachelor's, and then masters in the same subject. So how large could it be? I just read it once. Suppose 100,000. That will
Hmm.
suffice.
Okay.
And maybe depending on cases, um, for example, if we are talking about a race, smaller the time is better the person. And if we are talking about like it may be vice versa. Sometimes more time is the winner, sometimes lesser time is the winner. So that would depend on the case, the sensitivity, the given probabilities.
Okay.
Calculate the experimental probability of spinning a number 3. So may I say this is, yeah, sure.
26, 60.
26 by 260.
So
So
1 out of
that
10.
1 out of 10. Number 5,
39 out of 260.
39 by 260. And I'm looking forward to my calculator in this case.
Mm-hmm.
And I'm getting 3 by 20. Good thing is you'll always have your calculator with you.
Wait, so is it allowed on both sections? But
Yes,
okay.
P1, P2, P3, P4. We are doing P2 and P4.
Mm-hmm.
This is extended. P1 and P3 is core. Extended has is more syllabus than core. And in extended, it is possible to achieve alpha, A grade. In
The
core,
highest?
uh, like A grade, B grade, C grade, D grade, and so on. So that's A and A star is possible in extended. But in core, the highest score is C, even if you score full.
Why?
That's easy and lesser in syllabus. You
Oh,
may
okay.
say that suppose mathematics is compulsory in grade 10 and 11. So one has to do it, one has to pass it. So they may opt for core. I don't actually remember it was AQA board or some other student was from Scotland, and he told me that he is doing easy biology. And I was surprised, what is that? So they had
So,
biology A and biology B. It was
um,
compulsory for them to study, but they had this different option that is some lesser syllabus. I was amazed to know that they made it compulsory, like one should be able to know in case of accident or emergencies what should do. They're calling the ambulance, but they should know what to do on spot.
y-
So that was more or less concerning to this.
wait, so they would have to take biology for that, not like health and like physical education?
That's their choice. If they want to go for medical, if
Hmm.
they want to become medical students, doctors, they have to take the full syllabus. But that
Include,
state, I'm forgetting that was a particular board. I think it was AQA. So uh, they made it compulsory that you have to study biology, but it is not a compulsion to study the harder part. To be promoted, so you have to do it. At my time in 2007, Urdu A was made compulsory.
sorry.
Education ministers, they keep on changing. So at that time, Urdu B, Urdu is a language. So we have Urdu A and Urdu B. A is harder, B is easier. So the harder
Mhm.
one was made compulsory at my time. Education minister at the time was focused on something and he made that decision. Then there were times that additional mathematics was half credit. Now it is full credit. That's a complete subject. So policies, they keep on changing more or less. What you are going through, what other students are going through are 6 to 8 compulsory subjects, which are all full grade. And then you'll have choices to make in your A levels.
Mhm.
You,
So,
you,
course subjects and extended for the IGCSE. There's
yes,
a total of 4 papers. And for all of them, you can use
we are
calculator.
appearing only in two.
Only in two. Okay.
Yeah, 2 and 4.
Okay.
We will be doing 2 and 4. This book covers 2 and 4 completely. One who is doing extended can solve core very easily. But one who is doing core will not be able to solve all the questions of extended.
Because extended is harder.
A little harder and like 2 to 5% extra syllabus.
Mm-hmm. Okay.
In core, you may find these questions as well that make why the subject of formula.
Oh, so it's like pretty simple.
Yeah.
Very simple. Okay.
Okay. 2C, an odd number.
We have to add all of the probabilities with odd numbers, basically.
Very, very good. So we are looking at 1, 3, 5, and 7. 33.
131 over 260.
Yes. 131 over 260. It stays as it is. No cancellation. Last one. Factor of 8.
141 over 260.
That's right.
And that can be simplified with 2. And maybe
141 is odd, so it will stay there. Now, I don't know about you, how you did, but I chose to write this. I'm
in
not taking that risk that if I just skip any of the factor in my mind, I'll get a wrong answer.
okay. In my head, I was like doing like the fact is like crossing them
Yeah.
out.
There's no
Then it's
compulsion. You're doing it very good. There's no compulsion. Keep that in mind on exam day. Don't complain that you weren't sleeping. Okay. So fresh mind, practiced, you can do it. There's no compulsion. Whenever there will be, I'll definitely let you know that this is compulsory. We have to show these steps. And
okay.
in the test, the practice test or the questions which I'm giving to you, sometimes where I'm writing working, there is compulsory. It is me who's checking your paper, and I know you're working. I know your discussion. I know what you're thinking. And when I went through that question, I knew you would have done it. But the examiner is unknown. He
Mm-hmm.
may think you saw the answer on someone else's page. If working is not there for a 3 mark question, how did you get the right answer? Getting it?
Yeah.
So
So
I
we
know
have
you would have solved it somewhere and you wrote that answer. So
yeah.
showing the working is compulsory. Sometimes it
Okay.
is written on the first page of your exam paper that omission of essential working will result in loss of marks.
You always have to show you're working basically on these
Yeah.
like
Other than the word state, when it says state, no need to do the working and they are 1 mark question.
okay.
Okay. For example, these questions right here, this last part, 141 by 260. Now, the working would have been the one which you actually did. When you're doing something in your mind, when you're doing something on your calculator, just paste it on the page. That is the
Mm-hmm.
working. But in this case, you'll get full marks. 141 by 260. It is not compulsory. These are 1 mark question each. Question
Okay.
number 3. A consumer organization commissioned a series of tests to work out the average life of a new brand of solar lamp. The results of the test are summarized in the table. Life of lamp in hours and frequencies given. Calculate the relative frequency. Relative frequency is another word for probability. Relative frequency of the lamp lasting for less than 3000 hours, but more than 1000 hours. So less than 3000 and more than 1000 are these. And that is 75 plus 160 is 235 out of total is not given in the question.
So do we have to add them all?
Add the modulus.
So that'd be 300. Yeah.
And this simplifies to 47 by 60. If a hardware chain ordered, okay, now what is this in real life? For example, mm, let's say we have one more data and it shows us faulty lamps. Lifetime of, let us say that we are getting them manufactured and it's in front of you that there are 75 of the lamps which will glow more than 1000 and less than 2000 hours. And we have very less which are more than 3000. That's a very high quality. Let's say less than 1000 hour is rejected for us. So I may expect that 30 out of 300, like 1 out of 10 is faulty or rejected,
Mm-hmm.
1 out of 10. So if I am ordering 10,000 light bulbs, I may expect that 1000 will not be accepted. So if I'm ordering 100,000 light bulbs, I may expect that 10% of that 10,000 light bulbs will not be up to the standard.
Out of the total.
Yeah.
Okay.
So B part. If a hardware chain ordered 2,000 of these lamps, how many would you expect to last for more than 3,000 hours? More than 3,000, may I say it is 35 by 300
Mm-hmm.
of the total.
Yes.
And getting decimal number, that is 233.3. So I'm writing 234.
Mhm.
Okay, I just had a question in mind and skipped it. Okay, maybe it will come back. I was thinking of something. Research shows that the probability of a person being right-handed is 0.77. How many left-handed people would you expect in the population of 25,000?
So just 23% of 25,000.
Very good.
5,750.
5,750. Yes. Fifth, a flower enthusiast collected 385 examples of polynomialous mathematiculous flowers in deepest Peru. Just five of the flowers were blue. One flower is chosen at random. Find the probability that it is blue.
Well, 5 out of 385.
5 out of 385. Yes. And it is not blue.
380 out of 385.
This is one.
Bamboo.
We were talking about this, and we may have different approaches. One was 5 out of 385, and other is 380 out of 385, blue and not blue.
Mm-hmm.
And it was simplified to 1 by 77. And I was asking that if I directly write as 76 by 77. Now,
Yeah.
if it is 1 mark, yes, I may get the full marks. And what is it if examiner says show the working? I may write 1 minus 1 by 77 equals 76 by 77.
Okay. So you saying like simplify it first, so you don't have to simplify it later when you're doing it, so it's like easier.
Yeah, that was A part.
Mm-hmm.
So it is the case that 5 by 385 is 1 by 77.
Mm-hmm.
Question 6. A bag contains 9 equal size balls. 4 of these balls are colored blue and remaining 5 balls are colored red. Blue and remaining 5 are colored red.
Mm-hmm.
So, and the remaining 5, okay, find the probability that the ball is drawn from the bag is blue.
5 out of 10.
No, there are total nine.
Oh, five, four balls. Okay, so four out of nine.
Blue is four and red is five. So blue is yes, 4 by 9. Red,
Then five out of nine.
yes. It is neither blue or red.
Zero.
0 out of 9. Either blue or red.
Nine out of nine.
9 out of 9. So these are your favorite questions because they do not need working. You may answer them directly.
Very easy.
Question number 7. I think for today we will not have any homework.
Oh.
Like we'll complete these two questions and start from here tomorrow. A bag contains 36 balls. The probability that a ball is drawn at random blue is 1 by 4. I'm just extracting the data. How many blue balls are there in the bag?
Nine.
Very good. This will need working. 36 into 1 by 4 is 9.
Hmm.
Olive shuffles. Where is Olive? Olive shuffles an ordinary pack of 52 playing cards. If he then draws a single card at random, find the probability that the card is king.
Oh, so four out of 52.
That is 4 out of 52. A spade. I think I'll take a skip. This. I don't
Isn't
know
it
cards so
all
well.
four? Is it all four? Like all the options four?
No. Uh, okay. This is, if I remember that correctly. We have spades. We have
Mhm.
diamonds. We have four different types of things printed on the cards.
Mhm.
So, like, this is the diamond shape. It may be any number 1, 2, 3, 4, 5, 6, 7, 8, king, queen, something. And then this, and then something, and then something. So, it is, we have four different designs. So, this is 13 by 52 because diamond is on every number, then spade is on every number. And there are more options, black and red.
Mhm. So,
We'll
oh
do
yes,
this
there's
in
four. Yeah, yeah, yeah. And they'll be on different cards. So yeah, 13 out of 52.
and black. I think these are half of prime numbered card. Okay, prime numbers 2, 3, 5, 7, 8, 9. So these are the only. So 5, 1, 2, 3, 4. 4 into 13 by 4 into 4 by 52. And
So
we'll see.
there's four of the prime numbered cards and four of the even.
Yes. I'll confirm two things for today that if it is included in our syllabus, and then I'll give you the details of the cards as well. I just
Okay.
hope so they've eliminated it because books take time to update.
So they sued them and then they were actually successful?
That was Cambridge, and he raised a complaint and he was awarded those marks.
Oh, okay. Wait, so did they change it? So there's still going to be cards?
Now they
Like,
awarded the marks to everyone, and
Mm.
from the next syllabus, the question was eliminated.
Okay, so is it still eliminated?
That was Cambridge. This is
Oh, yeah,
uh,
yeah, okay.
I'll
Okay,
confirm. I'll confirm. Like it would hardly take me 5 to 6 minutes. I'll go through the syllabus again.
okay,
I'll share the syllabus with you.
okay. Is class over?
So we'll start from here tomorrow.
Mm.
Yeah, we still have 4 minutes if you need to ask anything.
Mm,
You want to ask anything?
no, because probability is not like that difficult because I've been doing it before, but no, I'm good.
Okay. We'll
Thank
just be doing probability, but different cases, sample space and tree diagram and something else. Independent, mutually. Okay, this will take a little practice. Yes. Two types are left, and then this topic will be completed. And cards are in syllabus.
Sorry?
The question related to cards,
Mm-hmm.
they're in
Oh,
syllabus.
oh, okay. Okay.
Okay, so this is the summary. We have like 13, 4 of each number.
Mm-hmm.
If we talk about 1, they are 4. We talk about 2, they are 4. We talk about 3, they are 4. So 4, 5, 6, 7, 8, 9, king, queen. I just asked someone about it. There are 13 and total 52. And then there are 4 patterns, diamond, spades, and half are black, half are red.
Mm-hmm. So, like the patterns, how many of the patterns are there?
4.
4 patterns. Okay.
Okay. Possibility diagrams. So it says the possibility space is a set of possible outcomes. One way is this, and one is the dot diagram we did yesterday. Last one would be the tree diagram. Worked example, 2 dice, 1 red and 1 blue are thrown at the same time and the numbers showing on the dice are added together. Find the probability that the sum is 7. So if we are throwing these 2 dice and we are adding them, we just filled it and the sum is 7. So
Yeah,
I can
6.
see, yes. So it is 6 out of 36, first step, and 1 by 6 is the answer. B part says the sum is less than 5. Sum less
6
than
out
5.
of 12 over 6 still.
So it is 1, 2, 3, 4, 5, 6, 7, 8, and 10. 10 out of 36. That will be 5 by 18.
Oh, so is it like instead
Sorry,
of
sorry, less than 5, my mistake. 1, 2, 3, 4, 5. Yeah. 6 by 36, that's 1 by 6. Okay. It says the sum is greater than or equal to 8.
mm, 15 out of 36?
15 out of 36 and 3 5 times 3 12 times. Last one says the sum is less than 8.
Oh, so 7 out of 12?
Very good. 7 out of 12, directly 1 minus the previous one. Okay, exercise. An unbiased coin is thrown twice, and the outcome for each is recorded as head or tail. A possibility diagram could be drawn as shown. Complete the diagram. So if we are looking at the first box, we can say head, head. And
Yeah.
second, we can say first row is head and second is tail. And first row is tail and second is tail. For this same concept, we can draw a tree diagram that looks like this. Suppose for the first row, we got head and tail. And then after this, we got head, tail, and we got head, tail. So if you just look at this, I have 4 different outcomes. Compare these two, this first one and the tree diagram. So when we look at this, 4 different outcomes. For the first one, may I say this is my first row and this is my second row? And when we write the possibilities, I would say head followed by head, tail, this is tail, head, and tail, tail. We do have the same possibilities. Copy and complete the diagram done. It says find the probability that the coin shows the same face.
2 out of 4, so 1/2.
2 out of 4 and 1/2. So 2 by 4 equals 1 by 2. If we look at the tree diagram, these two would be our answer. And how do we do that? Either we look at the final outcome or we use the probabilities. If I had to mention the probabilities, this is 1 by 2 and 1 by 2 at all times because probability is not changing. Now for the first one, head, we multiply this across the chain 1 by 2 into 1 by 2. So only to get head is 1 by 4. So 1 by 4 for all of these. And finally, the question was same. So we added these two.
Oh, so
The
because it's
coin
one,
shows, sorry,
because there's like 4 options, so 1 out of 4, and then you can just add them.
yes. Total will always equal 1. If you just add these two, they're 1. If you add these 4, they are again 1. Possibility, probability is always equal to, total is equal to 1. Okay, second part says the coin both show head.
1 out of 4.
So this is 1 out of 4. And if we look at tree diagram, that is again 1 out of 4. There is at least one head.
3 out of 4.
3 out of 4. There are no heads.
1 out of 4.
1 out of 4. Question number 2. Two dice are thrown and the product of the two numbers is recorded. Product is recorded. Draw a suitable possibility diagram to show all possible outcomes. Okay, for this, I'm going to draw the same 6 boxes and so on. And I'll try to fit in the given space. 3, another 3, 6, and threes and threes. So let me say these are the outcomes 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what are we looking at? We're looking at the product of both of these. So 1 into 1 is 1. We multiply it with 1. I just followed the sequence 2, 3, 4, 5, and 6. And 2, I'm doubling all of these 2, 4, 6, 8, 10, 12. With 3, 1, 2, 3, 4, 5, 6. So 3, 2 times 6, 9, 12, 15, and 18. 4, 2 times is 8, 12, 16, 20, and 24. 5, 2 times is 10, 15, 20, 25, 30. And 6, 2 times is 12, 18, 24, 30, and 36. Okay, the question. Find the probability that the product is 1.
1 out of 36.
Yes, 1 out of 36. The product is 7.
1 out of 36.
Where is it?
Oh,
Product
so
7.
0 out of 36.
0 by 36. So straight away 0. The product is less than or equal to 4.
5 out of 36.
Why 5? Why not 8?
Oh, sorry, I didn't count the 4. Yeah, equals
This
8 out of
8
30.
by 36 and 4 2 times, 4 9 times. The product is greater than 4.
Oh, so just subtract that by 1. So it should be 7 out of 9.
7 out of 9. The product is a prime number.
Eight out of 36.
I counted 6 numbers. I'm not counting 1.
Mhm.
So if we start from here, this is 2, 3, and 5. 1, 2, 3, 4, 5, 6.
Okay, so 6 out of 36.
6 out of 36 equals 1 by 6. The topic is easy. The only drawback for this topic is we make a slight mistake, we lose our marks. Because the examiner won't know our struggle. Even if you counted 8, that was parallax error or anything, but you did the struggle, and that won't be counted in this topic. The product is a square number.
One out of 6.
1 out of 6. You're actually fast. I'm still counting. So I'm looking at 1, 4, 9, 16, 25, and 36. So 1, 2, 1, 2, 3, 4, and 5, 6, 7, 8.
8
1,
out
2,
of 30. Okay.
so
Why am I
that
miscounting this? Well,
no issues, no issues.
I think,
We
oh,
we
okay.
do
Maybe I
have
should
some
copy.
limitations.
I
Yeah,
think I
yeah,
should
yeah.
copy down the document so like I can
Yeah,
like check it off when I do it.
yeah. We sometimes do have some limitations for this online class. And this is only like I'm writing it. If I would have a choice, I'll write it on paper and use my fingers so I don't make that mistake.
Yeah, okay. I have it.
Number 3. The diagram shows a spinner, 5 equal sectors, numbered 1, 2, 3, 4, 5, and an unbiased tetrahedral die faced 4, 5, 6, 8. 2, 4, 6, 8. The spinner is spun and the die is thrown, and the higher of the two numbers is recorded. If both show the same number, then that number is recorded. Either higher or same is recorded. Draw a possibility diagram to show the possible outcomes. Okay, so for the first one, I have 5 outcomes, and for the second one, I have 4. So we can draw 4 or 5 on either of the scales. We may have 2 different options. We draw those boxes, or we draw those dots. What are you doing? Squares or boxes or dots?
I'm doing squares.
Okay, then I'll go for dots and we'll see if we get the same answers.
So one of the spinners has 5, and then the other spinner just has 4, 8, and 9, or is that a 6?
2, 4, 6, 8. One is spinner, the other is tetrahedral die.
Okay. 2, 4,
1,
6.
2, 3, 4, 5 on spinner, and 2, 4, 6, 8 on the die. And we
Okay.
record either the larger number or the same number.
Okay. Okay. Yes.
So first part after doing this, calculate the probability that the higher number is even. You've drawn boxes.
Yeah, I've done boxes. For mine, like my first one.
We may have different representation, that won't matter.
Mm-hmm. Okay.
Okay. So I'm looking at the outcomes only, and I'm counting the even numbers. And once I started, I see that even are more, so I choose to count the odd numbers. 1, 2, 3. So I'm left with 17 even numbers. 17 by 20. What do you have?
Yes. 1, 2, 3. Um, I have 7, like I have 35 boxes, and I have 1 out of 5 for mine.
We cannot 35 boxes. Look at this. The first spinner has 5 options and the tetrahedral has 4. So 4 times is 20. See this?
Mhm.
When you get 1 on the spinner, you may get 2, 4, 6, 8 on the die. And if you have 2 on the spinner, you may get 2, 4, 6, 8 on the die. So after
Mhm.
every outcome of the spinner, we have 4 different options. Then again 4 different, then again 4 different. And this happens 5 times.
Can I quickly
So we
redo
have,
my boxes?
yeah, sure. I'll draw it with you if you say so.
Okay.
Now, let me know when you started, which side is the spinner and which side are the die, vertical or horizontal.
Oh, my die is vertical and my spinner is
That is
horizontal.
vertical. So we have 2, 4, 6, 8 this way. And the spinner is
Oh,
horizontal. So 1, 2, 3, 4, 5 like this.
yes.
So now see, these are going to be your outcomes, which you've already done. And what are we going to record? We are recording the larger number or the same number. So out of 2 and 1, larger is 2. And we know that 1 is always smaller, so I just quickly copied it. Then I'm looking at 2. Both of these are same. We record them. And then I record the larger one. Then we're looking at 3. 3 is greater than 2. Then 3 is less than 4, 6, and 8. Now we're looking at 4. 4 is greater than 2, so we record that. Then 4 and 4 are same, and 6, 8 copied. Now 5 is more than 2 and 4, but less than 6 and 8. So we
Mhm.
record these numbers, which are greater. And now the first part of the question was the higher number is even. What is the probability that the higher number is even? So we count the even numbers, and the numbers in red are 20 in total.
So, wait, there's actually three odd numbers, right?
Yeah.
Yeah, one, yeah, five, five, and three. Okay. The number is a multiple of three. Six out of 36. So one out of six. What?
6 out of
No, no,
20.
no, no. 20. 6 out of 20.
6 out
Sorry.
of 20.
20. Okay, yeah, 6 out of 20.
6 by 20, and we will simplify it to 3 by 10. Okay. Fourth one says the higher number is prime.
Five out of 20.
Correct.
One out of four.
5 out of 20 is 1 out of 4. The higher number is more than twice the smaller number. More than twice the smaller number.
Seven out of 20.
I counted 6. Let's see. If I look at the first number, more than twice, I'm looking at this one only. So double of it is 2. So it should be more than 2. So 3. And then I'm looking at this 2. Double is 4. So more than 4 are these two. two more. Then when we look at 3, I select only 8. When we look at 4, I do not select anything. At 5, I do not select anything.
So it's
So
going to
these
be
are 6 numbers which are more than half of the larger number.
so 6 out of 20.
More than half of this model. Yes. 6 out of 20.
Hmm. 6 out of 20.
6, 3 by 10.
Okay.
Questions will be easy. These just require a little patience. An unbiased cubical die. Unbiased cubical die has 6 faces numbered. These 4, 6, 10, 12, 15, 20. The die is thrown twice. The highest common factor of both results is recorded. Okay, this is going to be something. Draw a possibility diagram to show the possible outcomes. Hmm. This question is something. Unbiased die has 6 faces numbered 4, 6, 10, 12. 4, 6, 10, 12, 15, and then we have 24. The die is thrown twice. The highest common factor of both the result is recorded. So die is thrown twice. 4, 6, 10, 12, 15, and 24.
Okay.
Okay. So we've recorded HCF of both the numbers. Now we look at the question statement.
Can I quickly check my answers?
Yeah, sure.
Yeah.
I'll speak. Going vertically.
Mhm.
422414.
Nice. Okay.
If you ever
How
get a
far does
difference,
it
I may
go?
also.
Wait, does it?
Sorry,
Oh, it goes up to 24?
it
Oh,
goes
okay.
up to 20.
Okay, okay. I'll quickly do 24 as well.
You did up to 15?
Yeah, I did up to 15. I didn't see the 24. Okay. Okay.
Okay. So vertically, we have 422414.
Mm.
Second, second row, 262636.
Second row?
Yeah.
Oh yeah, yeah, yeah. 262636.
Third row, sorry, column vertically.
Two.
Under 10, it is 22 10252.
Okay.
Below 12, 462 12 3 12.
Okay.
Then under 15, 135 315 3.
315 3. Yeah.
Last line, 462 12 3 24.
Okay.
Can you see they are actually the reflection of each other in the diagonal form?
Five,
I'm
six.
looking at the first vertical line, for this vertical line, 422414, and then you look at this horizontal line.
Okay.
So once we start writing, it is actually half of the task we have to do.
It's basically it's exactly the same.
Yeah, because we have them as same, the options were same. In the previous question, the options were different. 2, 4, 6, 8, 1, 2, 3, 4, 5. The
If
outcomes were different. In this, we have outcomes as same.
this
Okay. So it says draw the possibility diagram to show the possible outcomes done. Calculate the probability that HCF is 2.
uh 10 out of 12.
Why 12?
I'll
There are
recap.
36 outcomes.
Okay, wait. 36. And then it's not 10 either. It's 9. Three,
At how many places do you see 2? Yeah, that's 9.
mm,
9 out of 36.
8. Wait. 1, 2, 3, 4, 7, 8, 9, 10,
You want me to highlight them?
Yeah, I think so, yeah.
You see, just go vertically and like count them as a tally. So 1, 2, no more 2 in the first row column, and then 3, 4, 5, 6, 7, 8, 9. Oh, another 2. 10. You were right.
Uh,
10 twos.
536.
Good. Feeling happy?
Uh, yeah, yeah.
Yeah, you should. You should. So this is 10 out of 36 is 5 by 18.
Like greater than 2.
HCF is greater than 2.
13 out of 18. There's 1 included in this. So it can't be that.
Can be
Okay.
that.
Yeah, there's 1 included. Mm, 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 13, 14, 15, 18, 19, 20, 23, 23,
I counted
24.
24. We have 10 twos, 2 ones, so that are 12, and remaining are more than 1 and 2.
24 out of 36, yeah. So 4 out of 6, so 2 out of 3.
HCF is not 7.
All of it.
All of
36.
it.
36.
36 by 36
Oh,
is
1.
1. The HCF is not 5.
So it would be 35 out of 36.
What about 34?
It's 34 out of 36.
Yeah, we have two fives.
And the 10. And then also in the 15. Oh, yes. Yes, sorry. Yeah, sorry. 34 out of 36, yeah.
Yep.
7 out of 18. Next one, 3 or 5. 8 out of 36. Yeah,
8 of 6, yes.
2 out of 9.
Last one. The HCF is equal to one of the numbers thrown.
Um, 15 out of 36.
I got
16 of
16. Let me recount. I'm recounting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 4 is same, 4 is same, 4 is same. Then that's a 6. 6, 6. 10, 12, 12, 15, 24. So 4, 4, 4. 6 is 10, 12, 15, 24, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. Did you find the 16th number?
Um, oh, yes. Okay. 16 out of 36. Okay. I need to learn how to count again. unfortunately.
just like it would be helpful if you use your lead pencil and just cross it out. But
Okay.
that too would mean that we are crossing it out 6 times. That would make it a little messy if we get a question of this
Hmm.
difficult level. Okay. Two dice are thrown and the result is obtained by adding the two numbers shown. Two set of dice are available. Set A, one dice has four faces numbered 1 to 4 already drawn, and the other 8 faces numbered 1 to 8. So two dice is 1 to 4 and 1 to 8. We are doing something in set A, then we are doing something in set B. And what is set B? Each die has 6 faces, 1 to 6. Copy and complete the possibility diagram below for each set, and we are adding these.
Okay.
Meanwhile, I'm writing the answers. Okay. There's nothing else in this question. We just have to fill in these.
Oh, okay.
I was expecting few parts which would require further questions. You can skip it if you wish. We can go to the next
Oh,
question.
okay. Because it's just adding.
Yeah. B part says in an experiment with one of the set of okay, we have a B part. One of set of dice, the following results were obtained. Okay, the results are given. Die scored 2 and 2 was seen 15 times. 3 was seen 25 times and so on. By comparing the probabilities and the relative frequencies, decide which set of dice was used. In an experiment, one of the set of dice, the following results were obtained. Dice
So
scored 2.
so there was 15 times 2. They scored 2 15 times. So we just have to count each one till we get the same one.
We'll have to check it. Okay, how do we check it? Just see, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have these outcomes in both of the sets. And if I look at this 2 only, it is 15 times. Out of how much? I'm going to check that. 15
Hmm.
times out of how much? So I'm adding all of these numbers. So this is 15 plus 25, 44, 54, 68, 87, 66, 54, 43, 30, and 40. I'm getting 500. So 2
Yes.
appeared 15 times out of 500. And when I simplify, I get 3 by 100. Now, if I look at set A, 2 appears one time only out of 32. And when we look at set B, 2 appeared one time only out of 36. This is 0.03. 1 divided by 32 is 0.03125. 1 divided by 36 is 0.027. Both are approximately equal to 0.03. So I am going to check another value. Mm, I'm going for 6.
You're doing
1,
number
2, 3,
6?
5. 1, 2, 3. Yeah, I'm going to check for 6. Why so? I just compared A and B and I saw same number of 2s, same number of 3s, same number of 4s, same number of 5. But the number of 6 is different.
Okay.
So at that stage, we might be able to differentiate which one it was. So 6 is 68 out of 500. So 68 by 500 is 17 by 125. Now for set A, this is 1, 2, 3, 4. 4 sixes out of 8 fours are 32 is 1 by 8. And 1, 2, 3, 4, 5 sixes out of 36. 0.138. This is 0.125. And this is 0.136. So clearly it is closer to set B. So by comparing the possibilities and relative frequency, decide which set they used. Set B was used. Is it clear or should I explain more?
Oh no, because when you do like the fraction 17 divided by 125, it's 136. So we're just choosing which one the closest one is, right?
Yeah.
Okay.
Because that's the theoretical frequency which we are calculating, and in part B, this is the experimental frequency. But it would definitely be closer to the one calculated. Okay. Now combining independent and mutually exclusive events. This is easy, but it sometimes gets confusing. For example, okay, let's go through step by step. If you flip a coin once and the probability of it is showing is 0.5, if you flip the coin a second time, the probability of showing a head is 0.5, regardless of what happens on the first flip, even like this, where there are first outcome, there is no influence on the second outcome, are called independent events. I think we discussed something regarding this on the first day. If I choose to throw a dice, which is numbered from 1 to 6, there is a possibility that 5 may appear, and the possibility would be 1 by 6. Possibility of 1 would be 1 by 6, 2 would be 1 by 6, 3 would be 1 by 6, and 1 by 6 for all. But what would actually happen? Only one outcome will be there. All 6 may occur, but only one will occur. If we have a match, football match between two teams, both of them might be having probability to win, but only one will be the winner. So this is mutually exclusive. Mutually exclusive means both can happen, but only one will be the winner. Only one will be the outcome.
Okay.
So events like this, where the first outcome has no influence on the next outcome, are called independent events. For example, we throw it once and we get a 5. So probability is 1 by 6. Now we are going to throw it again. So the first count outcome has no influence. What will be the next outcome? Again, the
Oh,
probabilities are still the same, which is 1 by 6.
and then whereas like for example, they were to pick out like let's say a sock from a drawer, then they have to like
Yeah.
do like 12 socks in different colors. Then you pick one out, then the rest would like it would lower down the number. There would be less
You
each
lower
time.
down the number, the probability changes. And if the condition is that without replacement, we have these two cases, we'll be coming on that. But that's a very good example. If you put the socks back, if you have this condition, then again the probabilities would stay the same. So they are independent according to the given conditions.
Hmm.
So sometimes there can be more than one stage in a problem, and you may be interested in what combinations of outcomes there are. If A and B are events, suppose head and tail, we may consider head first, or we may consider tail first. If there are different students in class, few are considering head, few are considering tail. But at the end, you'll have your same answers, whatever event you consider first or later, just like the one we did for the tree diagram right here. So these were independent of each other. You see
Mhm.
the second head right here, the second head, it is 1 by 2. First one was one head. Now you see this head, probability to get this head is still 1 by 2, though the first one was tail. So they are independent of each other. So these are mutually exclusive and independent events. Okay. So sometimes there are more than one stages in a problem. You may be interested in what combinations of outcomes there are. If A and B are independent events, then probability A happens and then B happens. First A, like first head and then tail, or first tail, then head. We multiply these two. Probability of A into probability of B and probability of A and B. If we get the same results, these are independent events. Now, A and B, what does A and B means? A and B would mean both are happening
Oh, at the same time.
at the same time. But in case of head and tail, we know that both cannot happen. If we
So,
just draw a Venn diagram, do you understand what Venn diagram is?
uh, no, I don't. Wait, can you
Okay,
show me?
okay. Well, we'll discuss it in detail. That is basically part of sets and Venn diagrams. Let me show you. For example, if I'm talking about 6 and I'm talking about 10 and I'm writing the HCF of the factors. So this is 1, 3, and 6. 1, 2, 3, 6. And when we write up for 10, this is 1, 2, 5, and 10, right? So if I write the factors of 6 in this circle and I write the factors of 10 in the other circle, so 6 in blue and 10 in red. So I may write 1 over here because both of them have 1, then 2. And
Wait, did
for
you say
6, this
10
is
bracket? Sorry,
5
did you
and
say
10.
10
I'll repeat.
bracket?
I'll repeat.
Six, seven,
These are
five.
factors of 6 and these are factors of 10. You see, 1 and 2 are common between both of them.
Yes.
So this common section means and. I can say factor of 6 and 10 is 1 and 2. May I say factor of 6 and 10 is 1 and 2. So we do have something in common. And
Mhm.
when I say that factors of 6, my answer is 1, 2, 3, 6. When I say factors of 10, my answer is 1, 2, 5, and 10. If I say factor of 6 or 10, in this case, may I write 1, 2, 3, 5, 6, 10?
Mm-hmm.
So this is the difference between and or case. And is both, or is maybe.
So or in so
Like
is
head or tail.
and
We are tossing a coin and I
Mhm.
say head or tail. So that is possible. Is head and tail possible?
No.
So if we draw a Venn diagram for head and tail, it would look like this. They do not have anything in common. Only one occurs.
Hmm. So it can only be and if there is like something in common between them.
Yes. So probability of head and tail both is zero, but probability of head into probability of tail. So head is 1 by 2 and tail is 1 by 2, that is 1 by 4. So both of these sides, left hand side and right hand side, are not equal. So they are not independent. If this works out, left hand side is equal to right hand side, then we will say yes, they are independent events.
Sorry, could you re-explain?
Yeah, I'll do. What is when is your school opening?
It's
Roughly
open in 2 days.
in 2 days. Okay. So that would be like Monday,
Yeah, on Tuesday.
Tuesday.
Mhm.
So if I say that I will be going on a sports event, will that affect your probability to go to school?
No.
No. And if I say there will be a snowstorm in Canada, will that affect your ability to go to school?
Yes.
So when my probability is not affecting yours, like first event is not affecting the second one, is independent.
Okay.
I choose to stay awake at night will not affect your probability to go to school, but your family members might affect. You may miss the alarm because you were awake all night. So when one event affects the other one, they are not independent. I just thought of one more example that would be more suitable. For example, we are talking about a electric motor, or let's say fan,
Mhm.
electric fan. So there are two things. One is electricity, the other is motor of the fan. If I say there will be no electricity, will your fan work?
No.
So the probability to having electricity or not having electricity will affect the working of fan.
Hmm.
And if I say the fan is not working or the fan is working, will that affect the availability of electricity?
No.
No. So the one which depends on the other is dependent. One which is not depending on either of the cases is independent event.
Hmm.
And mostly both events, when they are not depending on each other, only then we have left hand side equal to right hand side.
So when
Don't be confused. Left hand side equal to right hand side. Probability to for head and tail, we cannot have and part as equal. That is always zero. But probability to get head is 1 by 2 and tail is 1 by 2. So we know that they are independent, not independent events.
so getting head and tail is not independent.
Not independent. Let me read this again. Sorry, they're not happening at the same time.
Mhm. Yeah, they can't happen at the
So,
same.
yeah, mutually exclusive. They cannot happen at the same time.
Mhm.
If I just fill this one as well, if we say that is a head or tail, may I say it would be one? head or tail.
Mhm.
And if we talk about head only, this is 1 by 2. If we talk about tail only, this is again 1 by 2. So that
Mhm.
is 1 equals 1. There are situations where it is impossible for event A and B to happen at the same time, just like head and tail. For example, if you throw a normal die and let A is equal to even and B is equal to even number and odd number. So we know even and odd cannot occur at the same time. We are throwing
Mhm.
a dice. They cannot occur at the same time. So then A and B cannot happen together because no number is both even and odd. At the same time, under these circumstances, you say that A and B are mutually exclusive. Both can occur, but only one will be the outcome. Head and tail could be the outcome, but only one will result.
So for or, it's adding them together, and then for
It's
and,
adding them together.
multiplying them.
Yeah. If I say 1, 2, 3, 4, 5, 6. So when I say probability to get odd or probability to get even, would actually mean we are talking about all of these. So in that case, that's 1 and probability of odd. So this was 1. Probability of odd is 3 by 6. Even is 3 by 6. So 1 is equals to 1. Mutually exclusive events. This is the formula. And independent events. That is the formula.
Example of the P
So
and B.
yeah, when we will have these equal, they will be independent events. For example, if I just tell you that there is an event, probability of A is 0.4, probability
Mhm.
of another event is 0.3, and probability of A and B to occur is 0.12. And I ask you, are they dependent or independent events? So we'll apply this formula straight away. Probability of A and B is equal to probability of A into probability of B. So I'm going to check. A and B is given 0.12. A is given 0.4. B is given 0.3. So when I multiply, they do come out to be same. So I say yes, they are independent events. Probability of A happening or not happening will not affect B.
Mhm.
So
But then
that
when
is independent events.
so for the head and tails, it's 1/2 for both of them.
Okay. For example, you talked about socks.
Uh-huh.
I'm bringing in trousers and shirts also.
Mhm.
So will this selection of trouser affect your selection of socks?
So,
So they're independent events. But
mhm.
if the condition is given that if a student chooses to wear black trouser, she will not wear a blue socks.
Mhm.
Now this is dependent.
I don't understand like the formula for the 0 equals to 1/2 times 1/2.
Zero was for the case when we were talking about head and tail
So there's no chance of them happening like,
happening together.
yeah.
And if we talk about or case like head or tail, so it is 1.
1/2 times 1/2.
Is 1 by 4.
Yes. So this is not like included in the formula, so it can't be in the formula.
Which formula are we talking about? The first one or second?
The first one, 0 equals to 1/2 times 1/2.
Okay, 0 is equals to 1/2 by 1/2. Is it true or false?
False.
False. So that means they are not independent.
So they're dependent.
They're dependent. This is a check. This is a check.
So getting head and tails. Yeah, this is so that one is a test for head and tails, right?
Yeah, or for any other option. Like it
Okay.
could be for the dice or it could be for the socks. Formula stays same for every event. This is just a check.
Mhm.
If
For
this formula works out, if left hand side is equal to right hand side for the given probabilities, we will say that they are mutually exclusive.
Okay.
And if this formula at the top works out, we will say they are independent. And if both are working, we will say they are independent and mutually exclusive.
But like, so head and tails, getting head and tails is a dependent
Okay,
event.
we've solved it for both of these. In the second formula, they are equal.
Mm-hmm.
May I say yes, they are mutually exclusive?
Yes.
Okay. Mutually exclusive means only one will occur. Both have the chance, but only one will occur.
Mm-hmm.
So yes, one is occurring, but both have the chance. How do I do? Left hand side is equal to right hand side.
Mm-hmm.
Now we're talking about the first formula. Probability to get head is 1 by 2. Probability to get tail is 1 by 2. So when we multiply these two, this is 1 by 4. And on left hand side, probability to get head and tail is 0.
Mm-hmm.
This formula fails. So I am saying they are not independent. They're depending on each other. Why is the probability of head 1 by 2? Because there's a second half of tail. Why is the probability of socks not affected by selection of trouser?
What is
Even
it?
if someone just picks up your bag and leaves, and there are socks left. First, there were trousers in your cabinet, now there's no trouser. So that will not affect the probability of socks because socks was not dependent on trouser, but head is depending on tail, and tail is depending on head. Okay, see, this
So,
is 1, 2, 3, 4, 5, 6. Why is the probability to get a 2 1 by 6? And if I choose another die, which is 1, 2, 3, 4, what will be the probability of 2?
1 by 4.
Changed because it is depending on the total outcomes.
Mm-hmm. So independent events are like when one thing does not have an influence on the other thing, like
Yes.
another thing happening, and then mutually exclusive is just like one might needs to be like chosen, but they all have the same probability.
Yes. We
Okay.
can say same and we can say they all have the probability to occur. For example, we
Okay.
are booking a cab to go to school and we have
Mhm.
three companies, company A, B, and C. Like if I talk about here, we have Uber, Cream, and Yango. So three companies, A, B, and C. And I know that where am I going to go? I would choose Uber or Careem because I know their reputation in my area. So I would know that if I am booking this company, there is a chance they will get late because they have the low rates and availability is less.
Mhm.
So selection of the company might affect that I will be late or I will be on time. So it is depending on that.
Okay, so that's dependent,
That's dependent.
but the
And
options are mutually exclusive. Like choosing one of the options is mutually exclusive.
yeah, both could occur. That is mutually exclusive.
Okay. So it's a
And the check,
dependent, so it's a dependent mutually exclusive event, basically.
if these two formulas give a yes, and then
Okay.
we can, because these formulas are not working on quantitative analysis, not working on quality, they are working on quantities. We will
Okay.
put in the values, we will put in the numbers. Let's see examples. Okay. Sarah and James are both taking a music examination independently. The probability that James passes is 3 by 4, and the probability that Sarah passes is 5 by 6. What is the possibility that both pass? So when both are passing, we just multiply them. Event 1 into event 2, just like a tree diagram. And none of them pass. We just multiply the probability of failures of both of them.
Oh,
Then
okay.
at least one passes, either Sarah or James passes. I was actually hoping to solve a question for dependent independence.
At least one passage. What would that be?
Okay, I'll show you. So we are talking about Sarah and James.
Mhm.
So we say Sarah passes and Sarah fails. Then we say James passes and James fails. And then we say James passes and James fails. So when we say, uh, you asked about the third one,
Mhm.
at least one passes. So at least one passes would mean Sarah and James both passed, or Sarah passed and James failed, or Sarah failed and James passed. So we have these three outcomes. If I just write the first one out of the tree diagram, this is SJ, and this is SJ dash, dash would mean not pass. So S dash and J, and last one is S dash and J dash. So at least one of these passes is the first three options. Last one is both fail. So if I have to find that, I can fill in the tree diagram. It said that the probability that James passes is 3 by 4. So this is 3 by 4 and this is 1 by 4. James 3 by 4, that is 1 by 4. And it says that Sarah passes is 5 by 6. So if it is 5 by 6, this would be 1 by 6. So we are talking about at least one passes. So we know that we need the first three. It is easy to calculate the last one and subtract it from 1. So I'm calculating the last one, 1 by 6 into 1 by 4. 1 by 6 into 1 by 4 is 1 by 24. So the first three must be 23 by 24. And if we wish to do all of these just for a cross check, if I look at the first one, is it 5 by 6 into 3 by 4?
Yes.
Then the second one is 5 by 6 into 1 by 4.
Yes.
Then the third one is 1 by 6 into 3 by 4.
Yes.
I'm simplifying. 15 by 24, 5 by 24, and 3 by 24. 15 plus 5 is 20 plus 3 is 23 by 24. So whatever approach we take, we get the same answer.
Okay.
D part says either James or Sarah passes, not both. So we are talking about second and third only.
So that'll
So
just
we
be
multiply.
okay. So that'll be 22.
That will be this. This into this. That is 5 by 6 into 1 by 4.
And then a 1
5
by
by
6,
6.
3 by 4.
Yes.
Okay.
So 5 and 3, 8 by 24.
8 into 20. Okay. Tree diagrams are like the best option for these questions, right?
Yes.
Like,
Yes, it is. Only
okay.
when we have many outcomes, for example, we did with 6 and 4 options for the die, then that won't be a better option. I'll quickly show you why. So if we have 6 options and then 4, so 1, 2, 3, 4, 5, 6, and then 4 means 1, 2, 3, 4 after every other branch. That would be 24 branches in total. So in that case, we use sample space or we use possibility diagram. Like this one, right above this, we have 36 different outcomes. So tree diagram is not a good option for this. We could have done like 4, 6, 10, 12, 15, and 24. 15 and 24. So 1, 2, 3, 4, 5, 6 branches, and then 6 after every one of these. So these will be 36 branches.
So depending on the different questions, like the tree diagram is good. But for like the mutually exclusive and independent questions, the tree diagram is the best, right?
Yes, mostly the examiner will guide you through. He'll
Okay.
guide you through that, draw a tree diagram or draw the possibility diagram. So that would be helpful.
Okay.
And it entirely depends on your practice. Examiner would have no like no specific requirement which method to use. No compulsions.
We just have to get the answer.
Yeah. Okay, I'll share these questions with you and then we'll inshallah discuss if there are any ambiguities.
Okay.
This question 4E.
Mm-hmm. No. 3E.
3E. David and Taj are playing cards. Devon draws a card, replaces it, and then shuffles the pack. Tej then draws a card, find the probability that, okay, we are talking about this. Devon and Tej are playing cards. Devon draws a card, replaces it, and then shuffles the pack. Tej then draws a card, find the probability that. So we just consider that it is a fresh pack of cards because he draws, but he replaces it back. So the total is not changing.
Mm-hmm.
Both
So still.
cards are red or both cards are black. So if David is drawing a card, half are actually black and half are red.
Mm-hmm.
And then he places it back. So total is not changing. And then let me say David drew a red card, replaces it back, and then Tej draws a red card again. Plus black, black. Two possibilities plus a red, black. Sorry, it says find the probability that both are red or both cards are black. I was just doing the total possibilities. So both red and both black, these are the conditions. So for red, 1 by 2 into 1 by 2 plus for black, 1 by 2 into 1 by 2. This is 1 by 4 plus 1 by 4, that's 1 by 2.
Oh, so we times the probabilities of both of them being red and
Yeah.
also both of them being black and we add them together.
If you
Okay.
consider the tree diagram, let's say the first attempt is for David and he drew red or he is drawing black. And then the second attempt is for Tej, a red, black, and a red, black. So we are actually talking about the first and the last branch. And the probabilities are 1 by 2 for each of these because the total is not changing. If we would have to change the total, then what will be the case? Then for the first player, it will be 1 by 2, half of 52 is 26. For the first player, it will be 26 by 52. And for the second one, now let me consider that we did red first. And if I'm drawing red again, then I'll be using 25 by 51. Red
So
is
if they're
reducing.
mixing it.
Yeah. And
So
the total is also reducing.
yeah. Oh, okay.
But what if we say red and then black? So red would be 26 and 52. Black would be 26 by 51.
Hmm. So it's
Well,
still yeah.
yeah, black was already there. So that's not changing. Clear?
Yes. And also F.
Okay. The
Oh,
cards
it's
are different color. So we already actually have it for the same color. So we can do 1 minus 1 by 2 is 1 by 2. This is F part. Or
one by
else, just look at the tree diagram and we can now choose different color, this branch and this branch, second and third. So that would be 1 by 4, 1 by 4, and then we add them. Across one branch, we always multiply. When we talk about two different branches, we add them.
Okay. Okay, thank you. That was it. I don't have any other questions.